Hi everyone, we are going to learn about the 7th lab experiment, that is design Verilog program for implementing various type of flip-flops such as SR, JK and D flip-flop. Flip-flop is a circuit that maintains a state until directed by input to change the state. A basic flip-flop can be constructed using 4 NAND or 4 NOR gate. Flip-flop is popularly known as the basic digital memory circuit. It has its two states as logic 1 and logic 0 state. A flip-flop is a sequential circuit which consists of single binary state of information or data. The digital circuit is a flip-flop which has two outputs and are of opposite states. In SR flip-flop, in the flip-flop with the help of preset and a clear, when the power is switched on, the state of circuit keeps on changing. That is, it is uncertain. It may comes to set Q is equal to 1 or reset Q bar is equal to 0 state. In many applications, it is desired to initially set or reset the flip-flop, that is, the initial state of the flip-flop that needs to be assigned. This thing is accomplished by preset and the clear. Flip-flop basically the edge trigger flip-flop, and particularly it is the positive edge trigger flip-flop. That means it will respond to input only at the rising edge of the clock. Now let's see truth table of this SR flip-flop. So its truth table is very similar to SR latch. So basically it responds to the input only at the clock transition, and in the remaining time it will hold the present state. So this is the truth table of this positive edge trigger flip-flop. If the present state is 0, then the next state will remaining 0. And if the present state is 1, then also the next state will remain same. That means whenever there is a no clock transition, then there is no change in the flip-flop output. Now at the rising edge of the clock, if both input S and R are 0, then this SR flip-flop will maintain the current state. That means the next state of the flip-flop will be same as the present state, or in other words, there will be no changes in the output of the flip-flop. Now at the rising edge, if S is 0 and R is 1, then irrespective of the present state of the flip-flop, the flip-flop will get reset. That means if the preset state of the flip-flop is either 0 or 1, then the next state output of the flip-flop will become 0. Similarly, the rising edge, if S is 1, R is equal to 0, then flip-flop will get set. That means in that case, irrespective of the present state of the flip-flop, the next state will be equal to 1, and the last input condition when both input S and R is equal to 1, if because for the input combination the output of the flip-flop will become indeterminate. So if the flip-flop is designed using the NOR gates, then initially when both input are 1, then at a clock transition the R bar and X bar will become 1. Therefore, both output Q and Q bar will become 0. Because as you know, when any one of input of the NOR gate is equal to 1, then its output will equal to 0. That means in the case both output will become 0. So now let us see the characteristic equation of this SR flip-flop. So this characteristic equation show that next state of the flip-flop in terms of present state of the flip-flop, and the current input, that means it is the expression of Qn plus 1. The next flip-flop is JK flip-flop. In JK flip-flops, the diagram over here represents the basic structure of the flip-flop, which consists of clock, clear and preset. So similar to the SR flip-flop, this JK flip-flop also has two inputs. And using two input we can change the output state of the flip-flop. Main use of JK flip-flop is we are rolling the input, that means whatever indeterminate condition in SR flip-flop, the state using here, and we are changed the indeterminate state to triggered state. We are naming that SR as JK. This is the structure for SR flip-flop. Only change make it for this JK flip-flop, we can change like this. Previous flip-flop we are not having these connections. The required output for sequential circuit in your next state only. Next statement means Qn plus 1. Here JK inputs may be anything. Here like J is equal to 0, 0, anything. The logic circuit of JK flip-flop here, Q output is connected back to the AND gate where this input is applied, and similarly this Q bar input is connected back to the AND gate where this J input is applied. So with this little modification, when there is say no clock transition, then there is JK flip-flop will retain its present state. Similarly, both input are 0, then also output of this AND gate will be 0. Likewise, when this J is equal to 0 and K is equal to 1, then at clock transition the output of this lower AND gate will be 0, but the output of this upper AND gate will depend on the value of Q. So if the Q is 1, then the output of the AND gate will be also 1. For the both possibility of the Q output will remain 0, or in other words the flip-flop will get reset to 0. Similarly, when J is equal to 1 and K is equal to 0, then at the clock transition the output of this upper AND gate will become 0, but this lower AND gate will depend on the value of Q bar. So if the Q bar is equal to 0, in other words if the Q is equal to 1, then this input will be equal to 0. When j is 1 and k is equal to 0, then the flip-flop will get set to 1. When both input j and k are 1, so whenever both j and k input are 1, then at a clock transition the output of these two AND gates will depend on the value of this q and q bar. So if the q is 1, then the q bar is equal to 0. Both input g and k are 1, then the output of the flip-flop will triggered. If q is equal to 0, then in the next state this q n place 1 will become 1. In other end, currently if q is 1, then the next state of the qn place will become 0. So this is the truth table of the JK flip-flop. The characteristic equation of the JK flip-flop, there are 3 variables in Qn, J and K, and for the 3 input we have total 8 different combination. So as we have seen, when both J and K are 0, then the flip-flop will retain its current state. That means if the Qn is 0, then this Qn plus 1 will also remains 0. If this Qn is 1, then this Qn plus 1 will be 1. Similarly, when these j is equal to 0 and k is equal to 1, then irrespective of the present state of the flip-flop, in the next state it will reset to 0. Similarly, if this j is equal to 1 and k is equal to 0, then irrespective to the present state of the flip-flop, in the next state the flip-flop will get set to 1. Likewise, when both j and k input are 1, then the output of the flip-flop will get to that means currently of this qn is 0, then the next state qn plus 1 will become 1, and other hand, if this qn plus 1 qn is equal to 1, this qn is equal to 1, then in the next state this qn plus 1 will become 0. As you can see here, this output qn plus 1 is logical for the 4 different input combination. This is the characteristic equation of the characteristic equation is qn plus 1 is equal to j q n bar plus k bar Q N. This is the characteristic equation of the JK flip-flop. Then the D flip-flop. D flip-flop is a digital electronic circuit used to delay the change of state of its output signal until the next rising edge of a clock timing input signal occurs. D flip-flop. The characteristic equation. So this characteristic equation it is basically the representation of the next state of the flip-flop in terms of the present state as well as the current input. So basically it shows the behavior of the flip-flop in the algebraic form. Let's see the characteristic equation of this D flip-flop in terms of the present state Q1 and D input. So here for the two variables Q1 and D, we have total 4 input combination. So for the D flip-flop, we have already seen that when this D input is 0, then irrespective of the present value of the Q1 in the next state, this Q1 plus 1 will remain 0. And likewise, when this D input is 1, then whether this Q1 is either 0 or 1. In the next state, Q1 plus 1 will remain 1. So clearly as you can see, this Q1 plus 1 is same as D input, and we can say that this Q1 plus 1 is equal to D. So this is the characteristic equation of this D flip-flop, and this is the circuit for D flip-flop. This is the Verilog code for the SR flip-flop. This is module. In this program, the module has a keyword and it is a module name, and these are the input and output variables. The input variables like S, set, reset, clock, reset. The output variables are Q, QB, and the function always add and operators begin. Here we are written the cases of the execution of this code, and finally close with the end module. This is the output of this SR flip-flop. Here the given input, the S is equal to 0, R is equal to 0. Then the output we get X, and this is the Verilog code for JK flip-flop. Here this is the module name, and these are the input and output variables, and these are the input variables, these are the output variables, and here we have written the cases of the execution of this code, and this is the output of the JK flip-flop. and here j is equal to 0, k is equal to 0, and the output we get x and x, and this is the Verilog code for D flip-flop. Here the module, this is the module name, these are input and output variables, these are the input variables and output variables, and function always at, and operators begin, and these are condition. Cases of the execution of this code. This is the output of this flip-flop. This is the output of this execution. Finally, overall flip-flop are a usual and versatile type of digital circuit that can be used to store data, provide timing signals, and synchronize two separate clock signals. Thank you.